In a school gym in Orting, Washington, children are practicing how to outrun a mountain. The mountain is 30 miles away. They have, at most, about 40 minutes. More than 100,000 people now live on ground that Mount Rainier has already buried in mud at least twice. The easy answer is that Rainier is a huge active volcano near Seattle. That answer is wrong, or at least incomplete. Its deadliest weapon isn't fire. It's ice and rotten rock. And it doesn't need to erupt to kill. This valley has been buried before. People keep rebuilding in the path. So let's start with where those children actually live, because geography is the whole story here. Mount Rainier rises to 14,211 feet, the tallest thing in the Pacific Northwest by a wide margin, close enough to Seattle and Tacoma that on a clear day it fills the horizon like a second sky. It is not some remote peak lost in the wilderness. It sits at the head of a set of river valleys, the Puyallup, the White, the Nisqually, the Carbon, that run straight down from its glaciers into the most crowded corner of Washington state. Those valleys are the reason the region is beautiful. They are also the reason it is dangerous. They point like barrels from the summit down to the suburbs, and whatever comes off that mountain does not wander. It follows the water. It goes exactly where the people are, and it isn't one lucky valley in the firing line. Different sides of the mountain drain into different river systems, which means almost every direction Rainier can fail and points at somewhere with people in it. A collapse of the west flank feeds the Puyallup, and the Carbon toward Orting, Sumner, and Puyallup. A failure on the north and east feeds the White River toward Auburn and Kent. The south drains down the Nisqually. And the Puyallup doesn't just pass through suburbs. It empties into Commencement Bay at Tacoma, where the city's working port sits on ground built up from that same river's sediment. So the target isn't a town. It's a chain of towns, a string of school districts, and an industrial seaport, all lined up along channels that run directly back to the ice. That already changes the question. When most people picture a killer volcano, they picture the eruption, the ash column, the glowing lava, the pyroclastic cloud rolling over a town. And Rainier can do a version of that. It's an active volcano. It has erupted repeatedly over the past several thousand years. It still has heat inside it, and it still vents steam at the summit. Geologists put it on a short list of the planet's most closely watched volcanoes, one of only 16 so-called decade volcanoes singled out for study precisely because they sit close to large populations. But here's the strange part, and it's the part that keeps scientists up at night. The thing they fear most is not an eruption. It's a quiet morning. A morning when nothing seems to be happening at all. To understand why, you have to understand what Mount Rainier is actually made of. From the outside, it looks like solid rock and permanent ice. A fortress. On the inside, parts of it are rotting. For thousands of years, hot, sulfur-rich gases from the magma below have been rising up through the volcano and meeting groundwater trapped in the rock. When sulfur gas dissolves into water, it makes sulfuric acid, and that acid has been sitting inside the mountain, slowly eating it. It leaches the hard minerals out of the volcanic rock and leaves behind soft clay, weak, slippery, and saturated with water. So a mountain that looks like andesite and granite is, in places, closer to a giant pile of wet, chemically cooked mud, held up mostly by the frozen shell around it. That process has a name. Geologists call it hydrothermal alteration, and at Rainier it's concentrated high up on the steep western flank, in a scarred bowl called Sunset Amphitheater. Now stack the second ingredient on top of the first. Mount Rainier carries more ice than any other mountain in the lower 48. 26 named glaciers, roughly 35 square miles of ice, close to a cubic mile of frozen water sitting on those slopes. The Emmons Glacier is the largest glacier by area in the contiguous United States. The Carbon Glacier is the thickest, around 700 feet deep. So you have weak, waterlogged rock, stacked at steep angles, thousands of feet up, and you have an enormous load of ice and meltwater pressing down on it. You don't need magma to move that. You just need one part of it to let go. When it lets go, it becomes a lahar. That word matters more than eruption for the people downstream, so hold on to it. A lahar is a volcanic mud flow, a slurry of rock, clay, ice, water, boulders, and shredded forest that pours down a river valley. It doesn't trickle. A large lahar can move at 40 to 50 miles an hour. It can be tens of feet deep, and as it runs, it scoops up everything in the channel and grows. It behaves like fast-setting concrete. And then, when it finally slows and stops, it does set. It hardens into a gray plain of rock and mud that can be dozens of feet thick. That's the chain. Rotten rock, loaded with ice, high on a steep slope, gives way, mobilizes into a flood of mud, and races down a valley that happens to be full of towns. Weather can trigger it, an eruption can trigger it, or nothing obvious can trigger it at all. The rock can simply reach the day it fails. If that sounds like an overstatement, look at what a lahar has already done to a real town in the modern era, on the other side of the planet. On the night of November 13, 1985, the Colombian volcano Nevado del Ruiz produced a relatively small eruption. It barely qualified as a major blast. But it was enough to melt part of the ice and snow on the summit, and the meltwater mixed with loose volcanic debris and poured down the river valleys. Hours later, lahars reached the town of Armero, roughly 40 miles away in the middle of the night. They buried it. Somewhere around 23,000 people died, most of the town. Killed not by lava, not by ash, but by mud moving down a valley from a mountain most of them could not even see in the dark. That is the exact mechanism that engineers are describing when they talk about Mount Rainier. A modest event at the top, ice, water, a valley, a town at the far end. Armero is not a metaphor here. It is the closest thing the world has to a preview, which raises the obvious question. That's a nice theory. But has this mountain actually done it? Has the weak rock ever really failed and reached the lowlands where people live? It has. And the first time we can measure clearly, the scale is almost impossible to hold in your head. About 5,600 years ago, the entire upper east side of Mount Rainier collapsed. Geologists call what followed the Osceola mudflow. This was not a small slide. The failure took the top clean off the mountain. Before that day, Rainier likely stood something closer to 16,000 feet, and the collapse is a large part of why the summit sits where it does now. And it sent an estimated 3.5 to 4 cubic kilometers of debris roaring down the White River Valley. Try to picture that volume. Enough rock and clay and ice to bury a city under a layer tens of feet deep. All of it moving at once, and because it was born from that acid-rotted rock, it was rich in clay, which meant it didn't behave like a rock slide that spreads out and stops. Clay holds water. Clay stays slick. A clay-rich flow stays liquid far longer and travels far farther than anyone would guess, hugging the valley and refusing to quit. This one traveled about 100 kilometers, all the way to the shore of Puget Sound. It buried the ground where the towns of Enumclaw, Buckley, Auburn, Kent, Sumner, and Puyallup now stand. Where there are strip malls and warehouses and school districts today, there was, one afternoon, a wall of moving mountain. And here is the reversal that reorganizes everything you assumed. The Osceola collapse was driven by that hydrothermally altered rock, the rotten clay. And the geologic evidence does not require a big eruption to have set it off. The disaster people brace for, the eruption, is not the disaster that actually reached the sea. The mountain did its worst damage the way a rotten roof beam finally gives out, quietly, structurally, from the inside. That's the first thing Osceola proves. Rainier can reach the lowlands without erupting at all. The natural hope when you hear that is that Osceola was a freak, a once in the history of the planet catastrophe, a number so old and so huge it can't really touch us. So let's test that hope, because the mountain already answered it. Roughly 500 years ago, the best recent dating points to around the year 1507, probably in late summer, though the exact year is still debated. A chunk of Rainier's western flank collapsed again. This one was much smaller than Osceola. It's called the Electron Mud Flow, named for a little community in its path. It came off the same weak western side near Sunset Amphitheater, and again there's no confirmed eruption behind it, just altered rock reaching its limit. The Electron Lahar poured down the Puyallup Valley for about 34 miles, spread across roughly 13 square miles of the valley floor, and in places it was more than 26 feet deep. It ran right over the spot where the town of Orting sits today. The same Orting whose children we started with filing out of the school gym. They are not rehearsing for a hypothetical. They are living on top of the last time it happened. You might reasonably ask how anyone can put a date on a disaster from around the year 1507, and the answer is one of the genuinely unsettling parts of this story. When a lahar buries a valley, it snaps off and entombs the forest that was standing there. Those dead trees don't fully rot inside the deposit. They're preserved, upright stumps in some places, a whole ghost forest sealed in hardened mud. Geologists dig them out, count and match their growth rings, and cross-check with radiocarbon dating, and from that they can read not just the century, but, in the best cases, close to the year and even the season a flow came through. That is how researchers recently narrowed the electron event to roughly 1507 in what was probably late summer. The trees are, in effect, a timestamp the mountain left in the ground. And they are why scientists can say, with real confidence, how often this happens. That's the second proof, and it's worse than the first. Osceola showed the mountain could do it. Electron shows the mountain repeats. And geologists have found that these clay-rich collapses have come on average every 500 to 1,000 years for the last 6,000 years. Electron was about 500 years ago. Do that arithmetic, and the calm goes out of the room. But there's still a way to keep it comfortably in the past. So let's take that comfort away too. 500 years, 1,000 years, that's still deep time. Nobody alive has seen this rock actually move. Right? Wrong. It moved in living memory, and it was photographed. On December 14, 1963, the north face of Little Tahoma Peak, a jagged 11,000-foot shoulder of Rainier, came apart. The rock fell onto the Emmons Glacier below, and when it hit the ice, it shattered and turned into a series of high-speed rock avalanches. At least 7 separate waves came down, something like 14 million cubic yards of rock in total. And they did something that sounds impossible. They ran more than 4 miles down the valley, dropping over 6,000 feet, at speeds geologists estimate topped 100 miles an hour. The reason they traveled so far is chilling in its simplicity. The debris trapped a cushion of compressed air underneath itself as it moved, and rode on that air with almost no friction, the way a puck glides on an air hockey table. The likely trigger was small, possibly a little steam explosion near the base of the peak, a minor nudge, a 4-mile avalanche. The only reason December 14, 1963 is not remembered as a mass casualty day is the calendar. It was winter. The upper valley, the campgrounds, the trails near the Emmons Glacier were empty. Had it been August, with hikers and climbers spread across that ground, the story would be told very differently. And that's the third thing this mountain proves, this time in modern photographs. The collapse mechanism is not ancient history. It is live. It happens now. It happened onto a glacier that, in summer, is one of the most heavily traveled routes on the entire mountain. And it isn't only the rock that turns dangerous without warning. Sometimes it's just the weather. On the night of October 2nd, 1947, after a day and a half of very heavy rain, the lower end of the Kautz Glacier collapsed and released a surge of water that ripped down the valley as a series of debris flows through the night, ending the next morning. No eruption, no earthquake, just rain hitting a glacier the wrong way. It moved something like 40 million cubic meters of material and buried the park road under about 28 feet of mud, rock, and shredded timber. If you drive into Mount Rainier National Park today and cross Kautz Creek, you are driving over that deposit. It is the most voluminous debris flow of the recorded historical period at the mountain, and it was triggered by nothing more exotic than a hard autumn storm, which tells you the trigger doesn't have to be dramatic. The mountain keeps a lot of loaded guns, and some of them go off in the rain. Because that's the other thing about Rainier. While it sits there quietly threatening the valleys, it is also, constantly, drawing people up onto the exact unstable ice that does the killing. Around 10,000 people attempt the summit every year. Roughly half make it. And the mountain that engineers fear for its rotten flanks is, to a climber, one of the great training peaks in North America. Glaciers, altitude, crevasses, the closest thing in the lower 48 to a Himalayan expedition. The danger isn't hidden from them. It's the entire point. Which sets up the question the valleys and the summit share. If this mountain can move without warning, can skill and experience and preparation actually save you on it? Go to the morning of June 21st, 1981, and you get an answer nobody wanted. A large guided party was on the standard route, climbing through the Ingraham Glacier, an ice fall, a frozen cascade of glacier broken into house-sized blocks called serics. 29 people were on the mountain that day with Rainier Mountaineering Incorporated, the main guide service. Most of them clients, many of them relatively new to climbing. This was routine. It's the normal way thousands of people reach the top. They were doing everything right, on the ordinary path, in the early morning window climbers use, precisely because the cold keeps the ice stable. Shortly before 6 in the morning, without any warning that anyone could have read, a wall of ice about 300 feet wide broke loose from the ice fall above them and fell around 800 feet. Guides higher up on Disappointment Cleaver, Day, Target, and Whitaker heard the crack and saw it come apart against the mountain. 11 people were killed. 18 survived. The ones who happened to be standing far enough to the side when the block came down. The line between living and dying that morning measured in a few yards of glacier. Rescuers reached the site, but the 11 were gone into the ice, and the crevasse was too deep and too dangerous to work. The recovery was called off. It remains the worst mountaineering accident in United States history. And here is the detail that tells you what kind of enemy this is. The bodies were never recovered. They were carried into a deep crevasse and buried under tons of glacial ice, and they are still there, decades later, moving downhill an inch at a time inside the glacier. A National Park Service Board of Inquiry examined the accident and reached a conclusion that is more disturbing than any finding of blame would have been. It ruled the collapse a random event that could not have been predicted, and it held the guides blameless. There was no mistake to fix. The ice did not wait for anyone to do something wrong. And that is the fourth hard lesson. On Rainier, expertise buys you a great deal, but it does not buy you a warning. Skill did not fail those climbers. The mountain simply moved on a schedule no human could see. So if raw experience isn't enough, the modern instinct is to reach for technology. Better forecasting, satellite phones, avalanche beacons, the little transmitters climbers wear so that if they're buried, rescuers can home in on the signal. Surely, with all of that, the mountain becomes readable. Surely the machines close the gap. Now go to late May 2014 and the north side of Rainier called Liberty Ridge. A steep, committing technical route, the kind serious climbers train for years to attempt. A guided team of 6 set out, 4 clients and 2 guides from Alpine Ascents International, an experienced and respected outfit. They were equipped the modern way. On the evening of Wednesday, May 28th, at around 12,800 feet, they checked in by satellite phone. They reported they were going to camp for the night at that elevation. It was a normal call, a team doing exactly what such teams do. That was the last anyone heard from them. When they missed their return, the search began. And this is where you learn what rescue on Rainier actually means. It is not a helicopter appearing overhead at the crucial second. It is people trying to reach a place that is trying to kill them too. Searchers flew the north face. They picked up signals from the party's avalanche beacons. But the signals were coming from a glacier at the base of the wall, about 3,300 feet below where the team had radioed in. The most likely explanation, though the exact sequence has never been confirmed, is that an avalanche or a fall swept the entire rope team off the upper mountain in the night and carried them down the face onto the glacier below. And then the search hit the same wall the climbers had. Crews flew the face by helicopter and confirmed the beacon signals from the air, but the debris field sat in a zone of constant rock and ice fall, sliding and collapsing on its own schedule, and park officials made the call that no one wanted to make out loud. Sending people in on foot to recover the dead would only add to the dead. The recovery was suspended. The bodies were never recovered. It was the worst accident on Mount Rainier since 1981. 6 people in the modern era with satellite communication and electronic beacons, and the mountain still did not give them back. Sit with what that reveals, because it's the 5th proof and it points straight back at the valleys. The technology worked exactly as designed. The satellite phone sent the call. The beacons sent their signal. Rescuers received clear information about where the climbers were. And none of it mattered, because a signal is not a rescue. Knowing precisely where someone is does not shorten the distance, calm the ice, or make the ground safe to stand on. Communication improved. The physical problem did not move an inch. Hold that thought, and now bring it down off the summit and drop it onto a town of 8,000 people. To understand why anyone is watching this mountain so carefully, you have to go back to a single morning in 1980 at a different Cascade volcano 90 miles to the south. On May 18th that year, Mount St. Helens tore itself open, and the blast and its aftermath killed 57 people, including a young USGS geologist named David Johnston, who was at a monitoring post when the north flank collapsed. It was the deadliest volcanic disaster in the recorded history of the mainland United States, and it rearranged how the country thinks about these mountains. 2 years later, the USGS founded the Cascades Volcano Observatory in Vancouver, Washington, specifically to keep instruments on every volcano in the range: St. Helens, Rainier, Baker, Adams, Hood, and the rest. St. Helens taught volcanologists a lesson they carried straight to Rainier. The most dangerous thing a Cascade volcano does may not be the eruption itself, but the collapse of a weakened flank. That is precisely Rainier's signature. So the people watching Rainier already know what they're looking for. The problem was never knowing. The problem is time. Because that is exactly the bet the Puyallup Valley is making. After the science on Rainier's lahars became undeniable, a multi-agency effort in the mid-1990s built a lahar detection and warning system in the Carbon and Puyallup River valleys. It went live in 1998. It works on a simple, clever principle. A lahar shakes the ground in a very particular way as it moves, so sensors planted in the valleys listen for that specific vibration. The original system used devices called acoustic flow monitors, small instruments buried in the ground, paired with tripwires, tuned to the low rumble a wall of mud makes as it grinds down a channel. When the pattern shows up, computers evaluate it automatically and fire an alert to emergency managers who trigger sirens. No human has to be awake and watching. The valley itself is wired to scream, and they've spent the years since trying to buy back minutes. Starting in 2015, Pierce County and the Cascades Volcano Observatory planned a full modernization, and once funding came through in 2017, the USGS began replacing the aging 1998 equipment. Between 2017 and 2021, they installed 14 new monitoring stations, extended coverage beyond the Puyallup to the Nisqually and Tahoma Creek side of the mountain, added cameras, and wrote smarter software, the goal being not just to detect a lahar, but to estimate its location, speed, and size while it's still moving. So the warning tells people not only that it's coming, but how bad and how fast. It is genuinely impressive engineering. And it runs headfirst into a physical wall that no amount of engineering can move. Run that logic all the way down. A warning is only worth the time it gives you. The USGS estimate is that a large lahar starting high in the upper Puyallup Valley, one that begins the way Electron did, as a sudden collapse with no volcanic buildup to tip anyone off in advance, could reach the city of Orting in as little as 40 minutes. That is the number those school children are racing. 40 minutes from the siren to get every person in town across the valley floor and up onto the nearest high ground before a wall of mud arrives at highway speed. And Orting has a specific, cruel problem. It sits on the flat valley bottom, directly on the old Electron deposit, with two rivers between most of the town and the nearest hills. There is almost no high ground to run to, and the routes to safety cross water, so the community did the only thing it could. It started building a way out. An emergency evacuation footbridge, locals call it the Bridge for Kids, is going up across the Carbon River to give people, and especially school children, a walking route to high ground that doesn't depend on a road bridge that a lahar could take out. It has been in the works for more than 2 decades, and it is finally being built. Think about what that structure actually is. It is a bridge whose entire purpose is to let a town outrun its own mountain on foot. The drill is not a formality. It is the plan. There's the reversal that ties the summit to the suburb. On Liberty Ridge, technology delivered a perfect signal and could not deliver a rescue. In Orting, technology delivers a perfect warning and cannot deliver enough time. Same mountain, same gap, same lesson at 2 different scales. The machines tell you the truth. They just can't outrun the physics. And the physics, at 40 to 50 miles an hour down a valley aimed at your front door, does not negotiate. So step back and look at the whole system, because now the pieces lock together and the title stops sounding like hype. Geography built the trap first, a giant volcano parked at the head of valleys that funnels straight into a metropolitan area, so anything that fails at the top is delivered, with interest, to the bottom. Chemistry weakened it from the inside, turning solid rock into waterlogged clay high on the steepest slopes. Ice loaded it. 35 square miles of glacier pressing down on that rotten shell. History proved it fires on a human timescale. Osceola more than 5,000 years ago, Electron 500, Little Tahoma 60. Human ambition then did the one thing that turns a hazard into a catastrophe. It moved in. It built subdivisions, schools, and warehouses across the exact deposits the last flows left behind, and it sent 10,000 climbers a year up onto the exact ice that shears without warning. And distance did the rest, because when the moment comes, on the summit or in the valley, help is always too far, and the clock is always too short. And before you decide the people down there are simply foolish for living on a floodplain of catastrophe, look closely at why the ground is so attractive in the first place. The valley floors are flat, wide, well-watered, and easy to build on. But that flatness is not natural river bottom. It is lahar. It is the smoothed, level surface that Osceola, an electron, and a dozen older flows left behind when they spread out and hardened. The very quality that makes the land valuable. That broad, buildable flatness so close to Tacoma and Seattle is the fingerprint of the disaster. People didn't move into the path of the lahar by accident. They moved onto the lahar because the lahar built the most convenient real estate in the region. Dangerous because it's valuable, and valuable because of exactly the thing that makes it dangerous. That is the trap closing in slow motion, one building permit at a time. That's the answer to why scientists fear the quiet morning more than the eruption. An eruption announces itself. Magma has to rise, and rising magma sets off earthquakes and swelling and gas that instruments catch days or weeks ahead. Time to warn. Time to move. But a flank held up by rotten clay owes nobody that courtesy. It can fail on a clear day with a calm summit and a blue sky, the way it did in 1507. And the first anyone downstream would know is the ground beginning to shake in a way that is already too late to be good news. Nothing about that is settled or over. The rock is still there and still altering, acid still working through it, mostly on that western flank above the Puyallup. And the engine driving it hasn't switched off. At the very top of the mountain, steam still vents from fumaroles under the summit ice, warm enough to have hollowed out one of the largest networks of volcanic glacier caves on Earth. That steam is the visible edge of the same heat and sulfur system that has been cooking the inside of Rainier into clay for thousands of years. It is still cooking. The glaciers are still loaded on top of it. The valleys still run exactly where they've always run. And the towns are not shrinking. The Puget Sound lowlands are among the fastest growing regions in the country, which means every year there are more people living, sleeping, and going to school on ground that Mount Rainier has already claimed twice, and by every measure geologists can take, will claim again. Not maybe. When? The only real unknown is the date. And here's the final turn of the screw, the one that captures the whole problem in a single fact. Scientists have not been passive about this. They have flown Rainier with instruments slung under helicopters, reading the mountain's magnetism and conductivity to map where the solid rock ends and the acid-rotted clay begins. They have built three-dimensional models of the volcano's guts to find the weakest zones. And they have their answer. The biggest reservoir of collapse-prone, hydrothermally weakened rock sits high on the upper west flank, above the Puyallup, the same flank that produced electron. In other words, they can point at the part of the mountain most likely to fail and say, with a straight face, that is probably where it starts. They know the launch pad. They know the valley it feeds. They know the towns at the end of it. And there is nothing anyone can do to reinforce a 14,000-foot mountainside. All that knowledge, and the only defense it buys, is a siren and a head start. Which brings the whole story back to the same brutal arithmetic that governed a rope team on Liberty Ridge and a guided line in the Ingram Icefall. On this mountain, we have gotten very good at knowing. We have not gotten any better at reaching, or at stopping, or at slowing the clock. You can see the arithmetic in the everyday landscape if you know what to look for. Drive through Orting, Puyallup, Sumner, Fife, or any of the valley towns and you'll pass signs at the roadside, plain markers showing a route and an arrow, pointing the way to high ground, labeled as volcano and lahar evacuation routes. People pass them on the way to work and the grocery store without a second glance. They are the most ordinary objects imaginable, and they exist for one reason, so that when the siren goes, nobody has to think about which way is up. An entire region has deliberately organized its road signs around the assumption that one day it will have 40 minutes to leave. That is what living in the path actually looks like. Not panic. Just a set of small, permanent preparations woven so far into daily life that they've become invisible. So it comes back to a gym in Orting, and it comes back to a stopwatch. Every couple of years, the sirens sound on purpose, and the drill runs. In 2024, more than 45,000 students across the valleys took part, the largest Lahar evacuation rehearsal ever staged anywhere. The children file out of the building. They don't run in a panic. They walk, fast and orderly, along a marked route toward the only high ground within reach, while adults time them and count heads. They are practicing the oldest survival skill there is against the mountain, the same one the geology keeps teaching. Know exactly where the danger comes from, and know exactly how little time you'll get. Then, when the drill ends, they walk back down into the valley, back onto the old grade deposit, and go home. The mountain stands over them, quiet, white, beautiful, and patient. It has done this before. It is not finished.